Okay, hey everybody. I think I finally got this thing working properly. I see a couple of you out there. Good morning. Hope all is good and you're staying safe, staying socially distanced today. I finally got my streaming set up the way I wanted it to, and I think it's working now. Okay, so great. I don't know what that means about yesterday's stream, but well, that's okay. Sorry, just one second. I don't know how I can stay home and still get sick, but not quite sick yet. Okay, so today will be the lesson on rate law. This is a really important lesson as this is going to be informing directly into the next unit, which is the unit on equilibrium. And we are about, by my count, we are page 40 out of 60 pages. So yeah, so we're pretty much, this is the last leg of this unit. I feel like we've been in this unit for a while, so I'm happy to see it going away for a bit. So okay, just tell me if that still looks okay. Oh no, it doesn't. It does not like being small. Okay, I'm gonna just resize that. This is weird stuff. I have to have it at full size in one corner, and then let me see if I can move that to this other desktop. Will that work? Still trying to figure out the bugs and of this whole online process. Just waiting for it to catch up. See if it looks okay. Watching it bounce around here. Sorry, I'm watching the stream right now. Okay. Think we're okay. Yep, okay. All right, so as long as it stays there, it was getting kind of in the way of my being able to watch it. Okay, so a rate law is an expression, so that means like a function, like a mathematical function, a function, which relates the rate of a reaction. So that's what we've just been discussing earlier, right? The rate of reaction was concentration over time. To the concentration of the reactants at a given time. So rate law is not talking about, so previously, right? So in our previous section, we had said that rate was equal to a change in concentration over time, right? So that's what we did previously. Now the rate law is going to be relating the rate of reaction to the concentration of the reactants. So this is not going to be a change, not a change, not the change in concentration, right? This is saying that it's relating directly to the current concentration and how fast it will be going at a current concentration. So rate law helps us calculate the instantaneous rate of reaction when given the concentration of reactant and the reaction constant. So for the reaction A goes to products, we can say that the rate of the consumption of A is directly proportional to its concentration. That is, the faster A is consumed, so we're saying that rate here is going to be proportional to the concentration of A. That's the idea that when we know something about this, right? We know that the concentration of A will be going down over time. And the rate, which is the tangents to this curve, will be becoming slower sloped. So, so rate is proportional. Here we have a high rate. Rate is high, and the concentration of A is high. Over here, rate is low, and the concentration of A is low. So that's what they're trying to see. That's what they're using, is they're using that assumption, that assuming that rate follows one of these decaying curves, then then the rate is proportional to A. And if it's proportional to A, then we can make it into an equation where this change in rate is has a modifier that we call K. So this is a constant. This is going to be a rate constant. And then if we do some more plotting, we're going to find out that we also have to include some sort of exponent. If you have any questions, please feel free to drop them into the chat there. I am keeping my eye on it. All right, so we're going to say that this rate expression, so the rate law describes how the tangent on the concentration time graph slows has a decreasing slope over time as concentration decreases. Just gonna make that sized to the appropriate. I believe it's 18 or 16. Yeah. So if we were able to plot out the tangents of the curve, we could get a relationship between rate and A with a slope of K and an exponent of X. I mean, maybe slope is not the right word if it's a curve, but a modifier of K. I don't remember what they call that in math. Anyway, so that's the sort of math idea. So we could really use some data at this point. Maybe we can look at this data in the next question. So let's see. So this is also known as the initial rates method, or this is related to the initial rates method, which is something that also is, I think, missing from this booklet. But we'll go on the list of things to add to this booklet for next year, which I'm going to just grab a piece of paper here and try to find. Where? Oh, there. Okay, I'm going to make a note to myself. Kinetics initial rates. Okay, so if we plot out the tangents of the curve, we would get some sort of relationship between rate and the concentration of A, and then we could plot out that rate and how it changes over time. So what we're saying here is, if we said, I don't know what we're going to say. Well, I don't really have a good way of doing this right now, but maybe I'll come back with a little bit of a deeper dive on that at a different time. I'm going to put a little note here. Show a video on plot to rate law. Okay. Okay, so the order of a reaction indicates how the concentration of reactants affects the rate of reaction. The order is order of a reaction. A reaction is simply equal to x. X for the reaction equals the largest exponent. Okay. So for a reaction that has more than one reactant, such as A and B, then the products, A and B goes to product, then the rate law will become the rate equals the concentration of those two reactants raised to some power. This is because the overall rate of the reaction depends on both concentrations. The overall rate of the reaction depends on the concentration of both reactants. Each reactant may have a different exponent because it may play a different role in the reaction mechanism. All right, so this is where we go into some very fun, I think very fun, types of problems. And this is the standard setup, is you're going to get a table. That table will have a bunch of values in it, and we have to somehow figure out this equation from the values. There's a fast way to do this, and there's a slow way to do this. There's a slow and thorough way, which is probably the best way, but there's also a quick and quick way to do it that's probably a little easier. So I'm going to go through the very full explanation first, and then we'll go back and we'll see what we can if we can figure out a faster route. So the quickest route, well, maybe let's start with a full explanation. I think that's better. What do you think? Anybody feel strongly about quick or long? Anybody? One viewer? Okay. All right, I'll show you. So the idea is that we have these three trials, right? So we have trial 1, 2, and 3. In all of these cases, the rate law should be something like this: rate equals K times the concentration of H2O2 raised to some power times the concentration of HI raised to some power. And that's because in this reaction we have two reactants. We don't know what their powers are going to be yet, but we have done some experiments already. We've done what is known as an initial rates experiment. So the initial rates method, experiment method, finds the rate of reaction over a short period of time at the start of a reaction using many different concentrations of the reactants. Comparing these rates allows these rates over this same short time be used to determine the rate law. We could also find the rate law by measuring the concentration change over a longer time for a single mixture. But this is more difficult to measure. So there's sort of two options when trying to figure out a rate law. You can do the initial rates experiment, which is what we're showing right here. This is where we take multiple trials, usually 3, and change the concentration in each trial, and then compare the rate over a very short period of time, the same period of time for each of them. So we could measure for maybe a minute, or if it's a really fast reaction, measure it for 10 seconds. And just measure how much does the concentration change in these first 10 seconds. Okay, now change the concentration. How much does it change in these next 10 seconds? Change the concentration. How much does it change here? And then from there we could work out, we could work backwards, or we could use the table data to figure out what happens. Or we can take one chemical reaction and measure the change over the complete span of the reaction, and then plot it out and figure out the tangents at different points. But that can be also very difficult, and that one I would have to use probably like graphical software. With some graphical software, yeah, okay, it's not too difficult to measure, but it's much more effective and much quicker to get to the answer if we do these initial rates. So if I can think of a reaction I can do at home, I will try to record one for you and see if we can do one of these experiments on our live stream. So we'll see what that looks like. We'll see if I get there. Okay, so we have these 3 rates. So we know that in all 3 trials, the reactions must follow this pattern. So for example, trial 1, I could take this initial rate, 0.0076 moles per second, and I know it must be equal to some sort of K times, and I know the concentrations are 0.1 to the power of an x times 0.1 to the power of y. I also know that according to the table for my next reaction, I have a very similar setup, except my number is different. My number is 0.0152 molarity per second is equal to K times 0.1 power of x times 0.2 to the power of y. Okay, so that's interesting. Nothing to be gained there. And then 0.0152 molarity seconds equal to K to the power of times 0.2 to the power of x times 0.1 to the power of y. So I feel like the more you love math, the more you'll like this sort of unit or this lesson. So let's see how that goes. Um, so let's look at these equations and think about them, compare them to each other. So if we compare the rates, notice that the rate is doubled, right? This rate has gone by 2. Has anything else increased by 2 in our chemical reaction or in our equation setup? And we notice that, hey, these have increased by 2. So the number in the exponent has increased by under the exponent. What kind of exponent could that be where we would not have an effect? What am I trying to say? I'm saying that although this is multiplied by 2, there is an exponent. So if you did 0.1 times 2 to the power of y, it would still be affected by the y. So what does y have to be so that it doesn't affect the rest of the equation or rest of the expression? And so the answer here is 1. If y was 1, then this would not have an effect. This would be like multiplying by 2 to the power of 1. So another way, oh yeah, that's actually really good. If this is what we're doing, then this is the same as writing 0.1 to the power of y times 2 to the power of y. So whatever multiplier you apply here, whatever multiplier you apply to the concentration, it's like multiplying the entire equation by that multiplier of the concentration raised to the same power as that rate, that reactant. I don't know. That makes more sense. That makes sense to me mathematically. I'm not sure if that makes sense saying it out loud, but whatever. So what I want to think about is any change you make to the concentration will have an effect on the rate equal to that change to the same power that the concentration has in the expression. So this means in this case that y equals 1. Y equals 1 because this change here and this change here are the same only if y is equal to 1. Okay, so let's compare the next one. The next one we see also an increase in 2, so this is also times 2. And we also see a change of times 2. So this is times 2 to the power of x. So 2 equals 2 to the power of x if x equals 1. That's what we want to do. Let's do our purple one. 2 equals 2 to the power of y if y equals 1. And there we go. Now I got it. That'll work for us. So what we're doing here, this is the multiplier of concentration. And this one is the multiplier of rate. Now, this is a very specific example because in this example, notice that the opposite reactant, so for example, this one we just finished doing, this reactant stayed constant. So if the other reactant is constant, then you can do this kind of breakdown. There is another strategy to be used, an even longer strategy to be used in the case where that's not the case. Now I'll show you the very, very quickest possible one that you can do, which is quickest strategy is to look at the trials in your table and do something like this. This is times 1, this is times 2, this is times 2. This is going to be 2 to the x and 2 to the y have to be equal to 2. So what we're going to write is 1 to the power of x times 2 to the power of y equals 2. X to the power of anything, 1 to the power of anything is boring. It has no effect, so we can ignore it. So ignore. 1 to the power of x always just equals 1. And so then y equals 1. Repeat the process doing the other examples. So 1, so this is times 2, this is times 1, this is times 2. So 2 to the power of x times 1 to the power of y equals 2. You could even replace some of the values that you just figured out. So we just figured out y, so why don't we go in and replace the y with a 1. And now we see that, okay, well, that the 2 to the power of x times 1, that's just 2 to the power of x, and that is equal to 2. X must be 1, because only 2 to the power of 1, only 2 to the power of 1 will allow it to equal 2. All right, so now the final step is we need to get in here and finalize this equation, right? So the rate law is going to become rate equals k to the power of H2O2 to the power of 1 times Hi to the power of 1. And that's it. Now there's the value of k. That is the specific rate constant. Sometimes it'll also ask you to calculate that. That just is going to be a process of punching in those numbers. So we'll wait to calculate one of those when it asks. This is the rate law. This is the rate law. So it's a generic rate law. So that's your final answer. Probably would be nicer if it wasn't smashed in the middle of all this stuff, but that's okay. Let's try this next one. Okay, so for this next question, we have a lot of stuff going on. We have some major changes happening in both reactants. So we're going to have to be a little bit more careful with how we proceed. Usually, if I'm looking at a question like this, what I want to look for is a pair of data that are the same. So I noticed that in trial 1 and 2, that the value for B stays the same. So I'm going to compare those two. And I'm going to say that the concentration in A has increased by 3. Concentration in B has increased by 1. The initial rates has increased by 18 divided by 2. So what is that? Oh yeah, 9. Okay, 9. Oh, that's interesting. 9. Huh. That's not a one-to-one relationship anymore. So let's do this a little bit more formally here. Let's go down here. So we're going to go trial 1 and 2. And we're going to think about, we want to compare the concentration of A, let's call this A2, divided by the concentration of A in 1. And we're going to multiply that. This is all going to be to the power of x. This is just what I've been doing in that table, right? I'm going to use a dot just so the x's don't get confusing. the concentration of B, 2, concentration of B, 1, power of y, and that all has to be equal to rate 2 divided by rate 1. So if we take the ratio of any two trials, then we can ignore the k. If you really want, those of you who are wondering where did the k go, well, k is a constant, so it has stayed the same. If we divide k2 and k1, they're the exactly same value, so they cancel out. So that's the secret. Okay. So punch in some numbers. 0.3 divided by 0.1 to the power of x. 0.2 divided by 0.2 to the power of y equals 18 divided by 2. And that gives us a total of 3 to the power of x times 1 to the power of y equals 9. Anything to the power of y can be ignored because that's just equal to 1. Always, always, always. 1 to the power of 100, 1 to the power of 1,000, doesn't matter, it's always going to be 1. So what we're left with is 3 to the power of x equals 9. So 3 to the power of what equals 9? If you really need, you could use logarithms or something like that to solve it. But what is the answer there? Give you a quick second to think about it. I'm realizing that I've run out of space. Excuse me. How's everybody doing out there? Everybody feeling okay? Hope you're staying calm and collected. Hopefully you have decided that x must be 2, because 3 to the power of 2 is 9. So let's repeat this process with the other trial, the one where b is changing. So that'll be trials 1 and 3, maybe? Sure, 1 and 3. And so I'm going to do the same thing. I'm going to put 3 on top. So 0.2 divided by 0.1 power of x. 0.2 or 4 0.2 power of y and my difference in rate is 16, or my quotient of rate. My ratio of rates is 16 divided by 2. So the result is we get 2 to the power of x and 2 to the power of y is equal to 8. But it's not quite as dire here. We have two unknowns with the one equation. Because we did the previous example, we actually know that it's not 2 to the power of x, it's 2 to the power of 2. And 2 to the power of y equals 8. So this means that we can play around with this. This means that we've got essentially a 4 times a 2 to the power of y equals 8. Well, that means that we could divide the 4 away, and we are left with 2 to the power of y equals 2. Did I mention that this course fits very well with the pre-calculus course as well as an applied course? So I hope that you have a little bit of pre-calculus background. If not, then this might be a little bit of a tricky section, but mostly just the math is tricky. One option, especially now that you're at home, is to download a app called Photomath. And let me see if I still have it on my computer here. Yeah, I see it there. So this app here, Photomath, uh, we can scan a problem. So let's just say that we are at 2 to the power of, what was it? 2 to the power of 2 times 2 to the power uh, of y equals 8. So I'm going to just get that in here. Sorry about it being. And there you go. So it will solve it for you. Especially if you're having trouble with math, I would really recommend you get in there and look at how it solved it, and see if you can learn something about this sort of thing. Sure. So yeah, I really like Photomath. I have even allowed my students to use Photomath on their tests or on their assignments. Well, especially assignments, because I can't watch you when you're doing those. But tests in classwork, they can use Photomath because, I'm not trying to teach a math course, although we do have to use a lot of math in our university courses. And you'll be expected to be able to do it at university level by yourself, but, you know, um, right now, I want to get on to the learning part. So here what we have is we have a rate law that says that rate is equal to some constant times a raised to the power of 2 times b raised to the power of 1. Oh, yeah, y equals. What does that tell us? It tells us something, right? That this is really, we've discovered something very key to this chemical reaction. If you wanted to control how fast this if you wanted to control how fast this chemical reaction is happening, which concentration do you want to change? Should we change A or should we change B? Well, if we doubled B, the rate of the reaction will only increase by 2. If we double A, 4 times increase. Triple B, 3 times increase. Triple A, 9 times increase. So you get a way bigger difference in chemical reaction speed by adding more A. So if you have a reaction rate if you have a chemical reaction that has a high exponent for one of the values, then you have an advantage. You know something about how to manipulate this equation. Okay, so let's do example 3. Determine the value of the specific rate constant of K as shown in example 2. We don't do the specific rate constants in our rate law because this rate law actually applies to almost all systems. Even if it's hot or cold, this rate law, this will apply to this reaction at any concentration. And now is it the same temperature? At same oh no, at any temperature. So this rate law applies to anything. Now, once we figure out the rate constant, that will only apply to the system as we are currently using it. So whether we're using it at a high temperature or if we're using it at low temperature, but once we put in that little k, that is specifically to the setup that we have. So the specific concentration that or concentration and pressure we're using. So this is a set of conditions. So to determine the specific rate constant, all we do is we find one trial. So we can try trial 1. Trial 1. Take your rate equation. We know that the rate is 2 moles per second. And we know that we're going to be multiplying k times 0.1 to the power of 2 multiplied by 0.2 to the power of 1. And we're going to multiply those out. And the result is going to be that we're going to get k 0.1 squared. Again, if you want to use a photomath or a calculator, both are great options. So 0.1 to the power of 2, and then we'll just might as well do this together, 0.2. So we get 0.002. This does have units, and K will also have units. In this case, we have molarity and molarity inside of here. Molarity and molarity. So you're actually going to end up with molarity cubed. I'm not big on units for my K. I find that K in general doesn't have very good units, or doesn't really have traditional units at least. And so it's not particularly common to use to give it units. And so then we're going to take our 2.0 molarity per second, and we have to divide this by 0.002 molarity cubed. 0.002 molarity cubed. This is going to leave us with 2 divided by 0.002, which is going to be 1,000. And that's going to be molarity to the -2 seconds to the -1, something like that. So that's why it's really ugly units. I'm not going to be a stickler on units. It's all about magnitude for K. So there we go. That's our value. So we would be looking at the specific law, rate law, for the current conditions. I don't know what those conditions are. I'm just going to have to, there must be some sort of temperature, some sort of pressure. Maybe it's standard. Is going to be rate equals 1,000 times A times B. There's a square in there. Don't forget that square. And then you're done. So I find these fun. I think there's a little bit of a puzzle element to them, especially if you start just kind of eyeballing the table instead of making a excessive calculation. But excuse me. But it also depends on your comfort with math. Okay, so this is a big one. We got a big table now, and it says, hey, let's write out this rate law and then figure out some of the missing values. So let's see if we can do this by just looking at the table. So I'll show you what that looks like. I'm going to use multiple colors. I'm going to start by looking here, and I'm going to say, hey, look, all of these are increased by 1, by 1, by 1, by 2. This is increased by 2. So 2 to the power of x equals 2. Well, that's an easy one. That means that x equals 1. Okay, let's find another pair that works in a similar way. So now I'm going to change colors. Looking for a similar set. Okay, I don't see one that looks nice. I see a 5 in there. That doesn't look like very much fun. We don't have the rate for that one. Okay, so I do have a 2 here. Oh, wait, look at this. Okay, if I go 2 to 2, that would be times 1. And 1 to 1, this would be times 1. And then 1 to 2 is times 2. And these two are times 1. Ooh, that's a weird one. Okay, let's maybe write that one out because I think there's something interesting happening there. So if we compare trial 2 and 4, then the comparison will look like this. We're going to have, I'm just going to put A over here, A, B, C. So 2 and 4 is 0.2 divided by 0.2. B is 0.1 divided by 0.1. And C is 0.2 divided by 0.1. And they are equal 0.4 divided by 0.4. So let's go and solve this. This is 1 to the power of x, and this is going to be x, y, z. So 1 to the power of x, 1 to the power of y, times 2 to the power of z equals 1. That's really weird, isn't it? So we can get rid of the 1's, right? But both of these are useless to us. These are both just equal to 1, equal 1. So we're left with just 2 to the power of z equals 1. So what is z? If you're not familiar with exponents, this might be tricky. But there is a value for an exponent that has no effect on the value, or that always results in 1. So let me see if I can convince you of that. Check this out. If I do y equals x to the power of 1, I get an increasing value. If I do 2, I get an exponential value, 3. If I did negative 1, I get a weird value like this. But if I do 0, x equals 0, notice that the curve is one smooth line straight across. Let's just pump that up. So if x equals 0, it doesn't matter what the value is of the base, it will always be equal to 1. So what I'm saying is that for this question, if z equals 0, then 2 to the power of 0 is going to be equal to 1. And that is one of the options. So we have just said that this is 0. We just said this one was 1. So now we just have to figure out the last one. Oh, that's right. So the last one, let's use red here. So let's compare these two. Here is times 1, times 2, times 1, and 1.6 divided by 0.4, that should be times 4. So we are saying that that 2 to the power of, this will be y, and this will be z, this will be x. 2 to the power of y equals 4. That's the 4. This is the 2. 2 to the power of y has to be equal to 2. And that's our last one. So we're going to say rate is equal to k times a to the power of 1, b to the power of 2, and c to the power of 0. This can also be summarized as rate is equal to k to the power of a times b squared. We don't actually have to include c. What does that mean? Where is that coming from? think about the last lesson that we just did. What would be the result? Where would that C be disappearing? It means that C is not a part of the rate determining step. C is not in the reaction mechanisms in the rate determining step. That's really what it means. So we have a case where both A and B play parts in significant steps of the reaction mechanism, but C does not. C is part of probably the fastest step. The steps that include A and B must have similar speeds, and maybe B is part of a slower step. So the more B you put in, the faster the reaction goes, and that's it. That's what's happening. So we're getting evidence towards a reaction mechanism. That would require a little bit more thinking thinking and experiments to really drive into that. But that would be the idea. All right, we can calculate the rate constant. Once we have the rate constant, the rest of this becomes trivial-ish. So let's take that first one, 0.1, 0.1, 0.1, and a 2. So we're saying that 0.2, which is the rate, is equal to, I'm going to grab my rate law because I can't remember. Copy. Is equal to, this will be just trial 1. So is equal to K times 0.1 to the times 0.1 to the power of 2. And we don't have a C because, you know, if you want to think about it, you could put 0.1 to the power of 0 if you want. Do some multiplication or use an app, whatever you like. 0.2 times, let's go 0.1 times 0.1 to the power of 2. If you want to, we can see that's 0.001. Or if you want to include the C value, notice you can include it. As long as you put that 0 in there, it won't have an effect. Feel free to rewind if you want to feel like that proof is necessary for you. We gotta do some algebra to move the value over. 0.2 divided by 0.001, and we get 200 is equal to K. Probably has some units. I don't care. I just don't care about the units for K. It's a constant. It's only useful for that specific reaction. You should already know what kind of reactants you're using there. Calculate the rate for trial 5. Trial 5 has 3 values given, 0.5, 0.4, and 0.25. 0.5, 0.4, 0.25. And this one is squared. A, B, C equals rate. And we now have a K to put in front of that, 200. So I'm going to get my, and this is a 0. So I'm going to get my calculator out. 200 times 0.5 times 0.4 times, don't forget that square, squared times 0.25 to the power of 0 equals 16. And we know it's a rate, so that means it's molarity per second, which is our rate. I'm just double checking if you guys want to put any messages in the chat, that's great. If you want to let me know who's in that chat, then that is also excellent, so that I have an idea of who's paying attention. Calculate the concentration of A in trial 6. And so trial 6 is the one where they've given us the rates. The rate is 6. Okay, so in question 6 we have 6.00 molarity per second is equal to 200, which is our K, times A, which we don't know, times b, which I think is 0.6, and it's squared. We don't really need this last value, but I do want to keep putting the point that you can put it and it doesn't have any effect. 0.5 to the power of 0. Do some math. 200 times 0.6 to the power of 2 times 0.5 to the power of 0. Whoa. Okay, wait. 200 times 0.6 to the power of 2 times 0.5 to the power of 0 equals 72. So we've got 72 times a, and that's 6.00. So divide that by 72, divide that by 72. 6 divided by 72 equals 0.083. I believe that's 1/7. Is that not? Let me see. Nope. Oh, it's 72, not, okay, yeah. So 0.08, I think it's probably one extra decimal place there, is the molarity of A. Okay. All right, for the elementary reactions, such as a to the power a times a plus a, or where we have these coefficients, if they are elementary reactions, so this means reactions where we're talking about reactions that happen in one step. So, for example, one of these reactions is the reaction of smog in the reaction of ozone and nitrogen monoxide. The reaction is thought to happen in one single elementary step. In the case of an elementary step, we can skip everything. Is always Kelvin for T? Yeah, we pretty much have to use Kelvin. Yes. Yes. If we use Celsius, the Celsius, how do you spell Celsius? If we use C, then many of the curves are non-linear. Yeah, so I just saw a question in the comments about Kelvin versus Celsius. We haven't had to come across any temperature relationships right now, but if you do have to use temperature in calculations, we almost always want to use Kelvin because Celsius has negative values, and usually we're most interested in magnitudes. So if you multiply something by a negative value, then the magnitude will go up, like negative 100, right? The number's size will increase by 100, but it'll be negative. Whereas in Kelvin, negative 100 Celsius in Kelvin is 173, so the value will go down because the magnitude of the number has gone down. If that made any sense to you, great. Good news is that we don't have to do much with temperature lately. Okay, so if reactions happen, if they are elementary reactions, so elementary reactions are ones that happen in single steps. So elementary reaction equals single step reaction. So a single step reaction means no mechanism. Then in that case, the exponents will be equal to the coefficients. So here the coefficients are 1. Coefficients are 1. So we are going to be thinking about the rate as equal to K times O to the power of ozone to the power of 1 times nitrogen monoxide to the power of 1. We don't draw 1s, so I'm just going to erase them, but that's the final answer. I don't want to write final answer. Okay. So now if you have a reaction mechanism, then you can even use the reaction mechanism to determine the rate law by looking for the slowest reaction. So this reaction, elementary reaction that determines rate. So in this case, we can also say that the rate is equal to K times the concentration of M raised to the power of this 2. And that's it. That's the whole rate law, right? Only step 1 matters for rate. If we're using the statement that it's the slowest step, then it truly must be the rate determining step. So rate is determined by step 1, so now we are done with our reaction. So then what is the effect of tripling M? Well, tripling M means M to the power of 3. So if we are talking about rate is equal to K times 3 times M, power of 2, then that means that we are talking about 9K times M to the power of 2. I'm just taking that 3 out of the brackets with the exponent, and so that means we need 9 times rate. 9 times faster. Doubling N, no effect. No effect. Not in rate determining step. All right, that's a really important unit. I do realize that it's 9:58, so I will have to end the stream now. But please try to do the practice questions. I might post a practice problem sheet today, and you can print it off and take a picture and submit it online. But otherwise, we are apparently, even when we're not in the classroom and you're not there, I still go to the end of class, right up to the end. So I'm going to end the stream right now. Best of luck to you, and stay safe, wash your hands and all that, and we'll talk to you tomorrow. Thanks, everybody.